Smell a raw steak. Go on. It smells like meat. Maybe a little metallic. Nothing special. Now, cook it for 4 minutes. That smell, the one that makes people follow their nose across a restaurant, didn't come from the steak. It didn't exist 5 minutes ago. Not in the meat, not in the pan, not anywhere on Earth. You just watched chemistry create a flavor from scratch.
Here's the case file. For most of human history, we cooked food and had zero idea why it suddenly tasted better. We just knew fire did something. It took until 1912 for anyone to even start writing down what that something was. And even the guy who found it didn't fully understand what he'd uncovered. Today, we're solving it. And by the end, you'll find out this same reaction has a dark twin, one that can work against you.
For thousands of years, every culture on Earth cooked its way into the same trick without knowing it. Roast a coffee bean, and it stops smelling like grass and starts smelling like coffee. Bake dough, and it stops smelling like flour and starts smelling like bread. None of that is an accident. It's the same invisible process, wearing a different mask every time. But here's where it gets strange. Nobody could catch it in the act. You can't see a flavor molecule form. You can only taste the evidence after the crime's already happened.
That changed in 1912, when a French chemist named Louis-Camille Maillard noticed something odd happening when he mixed sugar and amino acids together and applied heat. He wasn't even trying to explain cooking. He was studying biochemistry. He stumbled onto the reaction almost by accident. And he still didn't get the full picture. It would take other scientists decades to realize this wasn't one clean reaction. It was a chain reaction. One chemical change setting off the next and the next and the next, branching in directions nobody could fully map. Which raises the real question this video is built to answer. If it's this complicated, why does it work exactly the same way on a burnt piece of toast as it does on a 5-star steak?
If heat is the trigger, the fix should be simple. Crank the temperature. More heat, more flavor. Right? Wrong. And this is where most home cooks get sabotaged without realizing it. Drop a wet steak into a screaming hot pan, and the surface doesn't race toward that perfect crust. It stalls. Because that water has to go somewhere, and turning liquid into steam eats up energy. Energy that should have been browning your food instead. So your hot pan is quietly losing the fight to a puddle of water you didn't even notice was there. This is why crowding a pan is a silent killer of good cooking. Pack it too full, and all that released moisture has nowhere to escape. The whole surface stays wet longer than it should. No steam room ever made a good crust.
And here's a myth worth killing right now. You've probably heard this reaction starts at exactly 140 degrees Celsius or 285 degrees Fahrenheit, like it's a light switch. It's not. It's more like a dimmer, controlled by temperature, time, acidity, and that word again. Too much water, and the reaction slows down. But bone dry isn't automatically better either. The molecules still need enough movement to actually find each other and react. So the real secret isn't hotter, it's drier at the surface on purpose. Pat that steak dry before it hits the pan, and you're not doing a kitchen ritual. You're rigging the chemistry in your favor.
Here's the part that should really bother you. Steak, toast, coffee, and fries are all running through the same general reaction. So why doesn't your morning toast smell like a ribeye? Because the culprit doesn't work alone. It works with whatever raw materials it's handed. Beef brings its own mix of amino acids and sugars to the table. Wheat brings a completely different set. Coffee beans bring their own. So when heat sets the same general chain reaction loose, it's not building from the same blueprint each time. It's improvising with different parts. Same crime, different evidence, different scene. And some of what gets built along the way is volatile, meaning it doesn't stay in the food. It escapes into the air and heads straight for your nose before you've even taken a bite. That's why you can smell coffee brewing from another room or catch the scent of toast before it pops. But, plot twist, not everything you're smelling is even from this one reaction. Caramelized sugar is doing its own thing. Melting fat is releasing its own aroma compounds. This isn't a solo act. It's an entire orchestra of chemistry happening on your food at once, and the reaction we've been chasing is just the loudest instrument in the room.
So what's actually happening under that crust? At the molecular level, it starts small. A sugar molecule bumps into an amino acid. They react and form something new and unstable. And that instability is the whole point. That unstable compound doesn't just sit there. It breaks apart. It rearranges. It collides with other molecules and creates more new compounds. One reaction becomes the fuel for the next. It's less like a single event and more like a chain of dominoes, where every domino is also on fire.
Some of what gets built along the way belongs to a family of compounds called pyrazines, heavily linked to that roasted, toasty smell you already know instinctively, even if you've never heard the word before. Others build up into large brown molecules called melanoidins, and those are quite literally the color of your crust. That golden brown shell on your bread isn't browned because it's dry. It's browned because it's covered in a specific class of molecules that didn't exist an hour ago. The crust isn't the food. The crust is the evidence.
So if we understand the culprit this well now, can we recreate it on purpose? That's exactly what's happening in food science labs working on plant-based meat. Making something look like a burger isn't the hard part. The hard part is making it behave like meat under heat, producing the right aroma compounds the second it hits a hot pan. Researchers mix combinations of amino acids and sugars, heat them under controlled conditions, and study exactly which volatile compounds show up, hunting for the specific combination that reads as roasted, savory, meaty to your brain. They're not inventing new chemistry. They're reverse engineering a reaction our ancestors triggered by accident over a campfire thousands of years before anyone knew what a molecule was. The mystery that started with a French chemist noticing something odd in 1912 has ended up in food science labs trying to recreate the smell of a campfire steak without the steak.
So next time something turns golden in your kitchen, you're not just watching food get hot. You're watching 100-year-old mystery solve itself, one molecule at a time. The same invisible chemistry that built the smell of coffee, the crust of bread, and the crave of a steak, quietly rewriting your food while you weren't looking. If this cracked the case for you, subscribe. The next episode chases a flavor mystery even stranger than this one.